Okay, so we are in question 1.2 for foundations of linear and generalized linear models. Where are we here? Okay, so it's a two-part question. So first we need to describe the function or the purpose of a link function, and then try to explain why the identity link function is not often used for binary or count responses. Okay, so first let's describe the function or the purpose of a link function. Okay, um, so so the book gives us well, the text in the book gives us a not so helpful answer, but it's true. It says that the link function connects the random component to the linear predictor. So the g of mu, so the mu, the expected value of our outcome transformed by the link function equals eta, or that's the linear component. Okay, um, but really what the link function is hopefully accomplishing is a couple of things. So it is true that it is connecting the random component to the linear predictor, although it's a little bit hard to see that here because where is the random component located or whatever. Um, but really what the link function is doing, or another way to think about this, is that the link function is transforming mu, the expected value of our outcome, so that it can be modeled with a linear predictor, and I'll show you what that means here in a second, and also to ensure that the error distribution conforms to the assumptions chosen in the model. So if we're looking at something like count data, so think about the number of crabs we expect to find by upturning stones on a beach. Okay, if you've never done that, it's a lot of fun. So this number, this count, cannot be negative, right? We can't find -2 crabs, right? We can find 0 crabs, or 1 crab, or 10 crabs, or something, but we can't find -2 crabs. Okay, so that means that our expression that we're going to use to model this has to only allow positive values. Okay, and so so it could be then that the expected value, one way that we could do this to ensure only positive values is to take our linear predictor, right, x beta. So if you don't remember, x beta just equals eta. Eta is just a shorthand for it. But we could take x beta, our linear predictor, and exponentiate it, right? Now we only have positive values. Okay. But the problem is that this is not a linear function, right? It's an exponential function. Okay. But that's no big deal because we can just take the log of both sides. Now we get the log of mu equals x beta. Okay. And now x beta is a linear function and it's modeling log of mu. And in this case, log of mu is the link function for this type of data. Okay. So hopefully that that helps resolve helps resolve this question. Okay. Part B is, why isn't the identity link so the identity link is typically used with a normal response, or often used with a normal response, but not usually used for a binary or count response. Why do you think this is? Okay, so the identity link function, if the identity is g of mu, well then it's just mu. So the identity link function is basically, it's not there, okay? It just says whatever mu is still that after you transform it with the identity link function, okay? So with a normal response variable, normal response variables are typically, at least in principle, unbounded or close to being unbounded. Okay, and so this is so it can take on both positive and negative values often, and there's no clear upper or lower bound. I think maybe that's a better way to say it. There's no clear upper or lower bound. Okay, so for example, if I'm measuring height across the population or something like that, height is often measured with a normal distribution, okay? And it makes sense because, so I say, okay, where should we draw the line? When is it bounded? When will we never find a taller person or a shorter person? It's not easy to draw that line. If I say, okay, I think that the tallest person is 7'6". Well, is there a 7'7" person out there? I don't know. Maybe I haven't seen a 7'7" person, but that doesn't mean it's not there. But so I don't want to just stop. I don't want to assume that that's as tall as somebody can be. Similarly, what's the shortest person that's going to be out there? Is it, 3'6"? I mean, maybe there's 3'4" people, or maybe there's 3'2" people, and so there's not a real clear place to draw the line, and so we can model that with a negative distribution. Okay, but in count data, as we've just seen, there really is a hard cutoff on the bottom side, right? There's no such thing as -1 crabs or something. Okay, so if we didn't transform, say, count data, our model would, in principle, be able to predict negative values of crabs. Okay? Now, similarly, for binary data is yes or no, and so we might model this by the percentage or the proportion of yeses to total responses. Well, that is always going to be bounded between 0 and 1, right? We can't have 110 yeses out of 100 responses, right? That doesn't make sense. Okay. So anyway, so binary data is also bounded. So if we use the identity link function, we would our equation, our regression, could predict values greater than 1 and less than 0, right? And so that's why it's typically not used for these. Okay.